This is module 9, verification part 2. The first couple of slides of this module are kind of the same as we had in the previous module. So just a quick summary. We talked about coverage analysis in the previous module. Talked about having a requirements coverage analysis on one side, and the other side we had structural coverage analysis. And in the latter analysis we look if we're going to try to find structures in the software, so lines of code in the software that were not exercised by the test procedures that we developed. So this is what we're going to focus on some more in this particular module. So a couple of definitions first. If I talk about an entry or exit point, typically what I mean is the point at which you enter a set, for example, a particular module, function, or unit. So if this is a particular module thrust reverse enable, that has the following low-level requirements within it, then of course this can be implemented as a function or a subroutine or whatever programming language you have. But the moment what you see here, if you look at the flow chart for this particular low-level requirement, you'll enter it, perform the if statement with the two else's, and then we'll exit. So this is the entry point and exit point. Now, okay, so what kind of structural coverage analysis are out there? There's a variety: statement coverage, decision, condition coverage, decision, condition coverage, multiple decision coverage, modified condition and decision coverage. So there's a variety of these coverage analysis out there. In ee6083, only 3 of those are specifically mentioned. The first one is the modified condition decision coverage, and we'll talk about this particular coverage analysis a little bit more. And you see that this particular MCDC coverage analysis only needs to be performed for level A software and with independence. The second one is the decision coverage. This one only needs to be performed with A and B, but also with independence. And then finally, you have statement coverage, which must be performed for level A, B, and C code, and then only with independence for level A and B. Now, we're also going to talk about the condition and multiple decision coverage as well, even though they're not specifically mentioned in ee6083. So what is statement coverage? If you look at the definition, statement coverage means that every statement in the program has been invoked at least once. Yeah. So first, if you write a set of test cases, then by executing these test cases, each statement in the program should be at least invoked once. Yeah. So for example, if I have a this C code fragment, for me to actually execute each and every line in this code, I need to make sure that I set up my conditions C, D, F, and G such that I'm executing the if statement, but also the else of the if statement. Yeah? So in this case, test case 1 should be C true, D false, F true, G false, and and this would result in this being true and that being true. In other words, procedure 1 being executed, and test case 2, which makes this one false, this one true, and the outcome of this end operation will be false. In other words, it causes procedure 2 to be executed. Okay. So every statement in the program should have been at least invoked once. And in this case, with these 2 test cases, that statement coverage would be achieved. Now remember, these test cases must be derived from the requirements, not from this little code segment. A couple things. Remember what I use here. I use the OR operation in C and the AND operation in C as well. So weaknesses are that this statement coverage really doesn't capture some of the robustness cases that you would. For example, suppose I have this low-level requirement. This is just kind of like pseudocode, and we've talked about pseudocode before in the previous module, so I'm not going to say too much about it, but it's one way to implement low-level requirements. Now suppose now one of the coders implements this low-level requirement with this piece of C code, and then see in this case he made a little coding mistake by actually, rather than saying larger than or equal larger than 0, it makes it larger than or equal to 0. But if you pick a test case where you say y is 2, for example, that would never find, the statement coverage would be successful, or there would be statement coverage, but it does not find this error. Of course, in this particular case, the error should have been found by a robustness test case. So this is an example why this statement coverage has some weaknesses. Okay, so besides statement coverage, we also have decision and condition coverage. In decision coverage, every decision in the program has taken all possible outcomes, and every point of entry and exit in the program has been invoked at least once. Decision coverage is required for software levels A and B. On the other hand, you have condition coverage, which means that every condition in the program has taken all possible outcomes, and every point of entry and exit in the program has been invoked at least once. Now, so what's the difference? So here we're looking at decisions, here we're looking at conditions. So if you have this statement here, this A or B together is a decision, A is a condition, and B is a condition. So every condition, because every condition must have taken all possible outcomes. So A must have been true and false, and B must have been true and false. In this particular case, every decision has to be true and false. So a decision is really a Boolean expression composed of conditions and 0 or more Boolean operators. So in this particular case, this is one decision, but it has 4 conditions. So one decision and it has 4 conditions, A, B, C, and D. In this case, the second example is again one condition with 4 conditions, A, B, A, C. Now you say, well, isn't that 3, A, B, and C? Well, you have to treat the A in this first portion different from the A in the second portion. So there are really 4 conditions. Of course, these 2 are referred to as coupled conditions. Okay, so if this is this is the requirement for decision coverage, there's 2 outcomes, like A or B must be true, A or B must be false. So one test case could be that A is true and B is false. And the second test case could be that both are false. If A is true and B is false, then the decision will be true because A or true or false is true. And if A is false and B is false, false or false, of course, false, so the outcome is false. So these would be the test cases for decision coverage. Now see, for condition coverage, you can pick a test case like A is true, B is false. A is false, B is true. So the conditions, A has been true and false, and B has been false and true. But what you see is, in this case, procedure 2 has never been executed, because in both these cases, the decision was never false. So this is one of the reasons why you don't see condition coverage mentioned that much. Of course, this doesn't mean, D178C tells you what attributes need to be in your lifecycle process. It doesn't mean you cannot perform a condition coverage. Of course, you can always do that. So this is another example here. Now, one thing is you can actually use proxies, but it's okay. Let's look at this particular if statement. Of course, this D larger than 0.5 is a condition. So this is A and B, where D larger than 5 can be either true or false. So this is really one condition. And E is smaller or equal to 0.7 is another condition. So if you call this condition A and this condition B, then this would really be more like if A and B. Alright, so there's also a thing called condition decision coverage, which is kind of a combination of condition and decision coverage. In this case, Every decision in the program must have taken all possible outcomes. Every condition in the program must have taken all possible outcomes. And every point of entry and exit in the program has been invoked at least once. Okay? So for example, if you have this low-level requirement, it would take 2 test cases to give condition decision coverage. Test case 1 would be true, true. Test case 2 would be false, false. So in this case, true, true would give you true or true is of course true, which gives you the decision coverage, but also decision coverage for true. And false, false will make the outcome false, and you see every condition, A has been true and false, B has been true and false. Yeah. Now, if you would pick your test cases like this, and a programmer or coder makes the mistake by interpreting this OR as an AND, you see, even though you reached condition decision coverage, this particular error did not get caught. Because true, true again results in this decision being true, procedure 1 being executed. And false, false will give decision to be outcome to be false and procedure 2 to be executed. So there is drawbacks on these kind of coverage analyses. There's one way to solve that is by saying I'm just going to try every possible combination of inputs to the decision. Yeah. Now, for example, you have an A or B. I can say, well, I'm going to try all different combinations. A can be true, A can be false. B can be true, B can be false. They're Booleans. So that means that there is 2 conditions. That means there's 2 to the power 2 is 4 possible combinations. So in this case, our test cases would be false, false, true, and true, true. Of course, you say, well, that's not that bad. You only have 4 test cases. But what you have to realize that for n inputs, multiple decision coverage requires 2 to the power n test cases. So if you look at, I think the Zielinski reference is available on Blackboard. You can take a peek at it if you want. But what you see in this particular table, you see the Boolean expressions taken from the airborne software in Ada of 5 LRUs from level A systems. So you see that some of these conditions, there is actually Boolean expressions there that have between 36 and 76 conditions. That means if you have 36, that means that you need to do 2 to the power 36 test cases. So that's a tremendous amount of work, hugely labor intensive, and hence not recommended. Okay, so let's look at another example here. Suppose we have this particular low-level requirement. Basically, we have an if statement that says if the weight on wheels and the airspeed is smaller than rollout upper limit, then you should enable reverse thrust. Otherwise, you disable it. Yeah? So we have one condition, weight on wheels. We have a second condition, airspeed smaller than rollout upper limit. Okay? Now, what you see, if you take this low-level requirement, I can implement it various different ways. The difference between coding option 1 and coding option 2 is that in coding option 2, I get rid of the else part by just setting reverse thrust to disabled right away. So for statement coverage, in this particular case, I would only need to test weight on wheels true and this thing true. And then I would have complete statement coverage. Whereas here, if I would only test a test case with weight on wheels true and airspeed smaller than rollout upper limit true, then I would not have statement coverage. Yeah. Of course, you look at this particular if statement, and as I said before, you need to use the requirements to drive the test cases. So in this case, I could have picked weight on wheels equal to true, and airspeed equal to false, and weight on wheels equal to weight on wheels equal to true, and airspeed smaller than rollout upper limit equal to true, and then one weight on wheels equal to true, and the second one equal to false. This would give me decision coverage. Of course, this wouldn't give me condition coverage. So then I would also have to set this one to false and this one to false. Now one of the things, oops,